My name is Dylan Dickerson. I'm a computer engineering major, and my project is comparing neural network topologies with mints. Neural networks solve problems in an interesting way by automating the learning process. An application of this is character recognition, which is being used for things like remote check caching, fraud detection, and natural language processing. The mints dataset is an interesting example of this, as it consists of handwritten digits saved as 28 by 28 arrays with values in each cell ranging from 255 for black to 0 for white. In our class, we learned about some types of neural networks, and this project applies a few of them to the mints dataset. This project utilized the TensorFlow library for Python and defined three types of neural networks: fully connected networks of differing number of perceptrons, autoencoders, and one LE convolutional network with two sets of convolutional and max pooling layers and one fully connected layer before the readout. All data collection was done on Microsoft Surface Pro, and TensorBoard was used to visualize the graphs, and all data analysis was done using Excel 2016. Further, the networks had some commonalities. Dropout was used immediately before the classification layer to keep the overfitting down. The activation function used was rectified linear units. The nets were trained for 20,000 steps on mini batches of 50 and record statistics on the test set every 10 steps. Classification error was measured using softmax and cross entropy. However, the autoencoders were trained to minimize the mean squared error between the input and output. All nets also use the atom optimizer to update weights and biases. But autoencoders are used to reconstruct the input. So, do they help with classification? Well, on their own they don't. Overall, they provide poor classification results. However, they're thought to be good for learning features by restricting the number that can be passed through the network via a bottleneck. So, if we feed the result of the encoding to another fully connected network, can they be used to speed up learning? Here's the architecture used for the fully connected networks. At each level, the double network has double the number of features on the output layer. The default network has around 500,000 parameters to learn, while the double network has around 1.3 million. Here are the networks that reuse the weights from the autoencoder shown later. Note that the one on the right has one extra layer that the default doesn't. These networks have around 1.3 and 1.5 million parameters to learn respectively. Here are the autoencoder networks, and other than the mid layer, the large network has double the number of outputs as the ones in the default. These networks have around 700,000 parameters and 1.7 million parameters respectively to learn. The convolutional network uses a 5x5 filter in both of the convolutional layers with same padding and a stride of 1. This network has about 3.2 million parameters to learn. Here are the results of running the tests. The convolutional network learns things very quickly and attains a 90% accuracy rate very easily. The autoencoder doesn't really go anywhere. The network based on the autoencoder's weights performs fairly well. With respect to training time, however, the convolutional network took nearly 30 hours to train, whereas the autoencoder took 2.5 hours and the fully connected network took 1.5 hours to train. Keep in mind, though, that the fully connected network shown here uses the output of the autoencoder after it's done training. So really, we could say that its time to train was 4 hours. And here's the comparison of the fully connected network shown so far. It's interesting to note that the preloaded layers actually do worse than the default and double layers shown earlier. Possibly this is due to the number of free neurons allowed in the network. And with the losses, we can also see that the default and double networks also attain lower losses much more quickly and stay lower. Here we can see the classification accuracy for the autoencoders, which never breaks 12%. And here's the error that the autoencoders were trained based on. Here are the results of running the autoencoders and the outputs they produce. After 0 steps, it's still very fuzzy. After 2,000 steps on the default network, the results are fairly good, but we don't see much of an improvement with the larger network. The takeaways from this project are that convolutional nets work very well to reduce the number of steps to hit a reasonable accuracy, while also keeping the loss low on spatially related data. It seems important to allow for more degrees of freedom as well within fully connected networks to make the accuracy better. The pre-training with the autoencoders didn't seem to benefit much, but this could have also been because those layers were locked in during the fully connected nets training. This project would have been possible without the help of the resources below in the Studio Code library for video production.